Okay, so good evening to all. Today we'll be having our 11th week NPTEL TA for the course TA session for this course Electrical Machines 1. So far we have discussed concepts of transformers. We started our session with transformers and then we moved to DC motors, and inside DC motors we discussed concepts on DC. First we started with armature, windings, machine construction and some terminology related to machines, DC machines, and then we moved to DC losses in a DC machine, and we discussed the power flow diagrams and some basic tests in a DC machines, and then we started discussing concepts on DC shunt motor. And shunt motor we saw how the construction will be and how the winding placement will be, and then we also discussed before DC shunt machines we started deriving the equations for DC motor torque, how the torque is being developed, and also the force derivations, and we saw those derivations as well, and those are the basic derivations which will be applicable to both shunt and series motors. And today especially we will start discussing about DC series motor, and we will see how a DC series motor looks like and how the winding is being placed, why is it called a series motor, and how the armature winding and series winding will be placed in a DC series motor kind of topology. And then we will discuss how the torque and back EMF equations applicable in this particular DC series motor case, and then we will see a numerical one or two problems on DC series motor, so that you will understand what we will be discussing now. So yeah, let's start. So this is a shunt motor. Last 2 weeks we discussed shunt motor only. So for example, I'll just show how our previous motor looks like. Okay, this is our motor armature. You can say these are the junctions of brush, and inside we will have armature resistance, and this is the back EMF. So these are the armature terminals. Now if it is a shunt motor, what happens in this shunt position, our field winding will be there. So because this is a shunt motor, so here the terminal voltage, like that, the supply will be there, and the motor will draw supply, and let's say this is total from the line current, that is from the supply, if the machine draws, and the current which goes through the armature will be armature current, and the current drawn by the field winding will be I shunt or I field, anything. This is the same. So this is RA and this is EB, plus and minus. So this is a shunt motor topology. Last 2 weeks we have been discussing shunt motor only, and now we will be looking at a different kind of topology, which is a series motor, where our motor will be there, same kind. So these are the brushes again, and this is armature resistance, and this is again back EMF. Oh, 1 second. This is the back EMF, EB. This construction will be same, but since it is a series motor, all these series, shunt, all these names are related to the placement of our field winding. Wherever you are placing your field winding, that's what you call your machine. So now, since this is a series motor, DC series motor, I am connecting my shunt winding, which was this one, which is previously in parallel to my DC machine, in series with the armature winding. Now so this is my, whatever we call it, R series. You can also call it as R shunt. Okay, R series or R field. Now same supply will be there. The only difference is the placement of my field winding. If it is in series with the armature, it is a DC series motor. If it is in shunt, then it is a DC shunt motor. So this is the only change. So apart from this, as a look back, just to brush up our previous week's discussion, So EB, that is the back EMF generated inside a DC machine, is equals to K phi omega, where K is a constant, we know phi is equal to 2 pi. There is some constant. Now from this you can say that since the machine is decided, K will always be constant. So EB will be proportional to phi into omega, where phi is the flux generated by the field current. So because whatever current flows through this field winding, that decides this flux, this winding. Here this is this winding. So here the current flowing is ISH through field winding. Here the current flowing is here the current flowing is I. So if you see here, inside shunt motor, the current division takes place along the shunt winding as well as the armature winding. Let's say IL current is equals to let's say IL is IL current, then the total IL current is divided into armature current and shunt current. So this is the relation in DC shunt motor. But if you see in a DC series motor, whatever current that is drawn by the machine, by DC motor, the same current flows through the series winding, that is field winding, as well as the armature winding. So that is because all the armature winding and series winding are placed in series. Now in this DC series motor, the relation is IL is equals to IA is equals to ISC. So all are same because my motor is in series. Now with that, that's the basic introduction about series motor. It's not that complex to understand. It's just placement of the field winding. Now yeah, this is the first equations we have derived for the past 2 weeks, and last week we have used this to solve some numericals on DC shunt motor, and now we are discussing it again. So EB, that is a back EMF developed inside the motor, and if you look about the torque, mechanical torque or electromagnetic torque developed, TE is proportional to K phi IA. Again, these K and this K are different. Let's say I denoted by K dash. This is also constant, but it is different from this K. These two are not equal. And yeah, it also depends on the amount of flux generated in the field winding. Let's say again that flux is dependent on the amount of current flowing through the field winding. So if you say if the BH curve is linear, you can say that this flux is proportional to whatever current that is flowing through the field winding. If it is a shunt motor, it is ISH, and if it is a series motor, it is ISC. So yeah, so basically what I mean to say is this flux is dependent on the amount of current flowing through the field winding. That is the important point. And yeah, since it's a torque, the torque is directly proportional to another component, which is armature current IA. You can see the back EMF is not dependent on IA, but the electromagnetic torque developed is dependent on IA. Why it is dependent and how this relation came, we derived it previously. 2 weeks back, we derived both EB and TE using the basic force equations principles and some basic laws in machines. So if you want to understand how this torque expression and back EMF expression came, you can refer to that session, or you can watch the sessions on YouTube. They are available. But for now we can't discuss it again because we have some topics to discuss. But still, EB is proportional to phi and omega, and torque is proportional to phi and IA. So this is the important thing to remember. Now yeah, so whatever may be, whether it's a series motor, shunt motor, separately etc., separately excited, compound motor, whatever it is, EB proportional to phi omega and TE proportional to phi I. So these equations always holds. So you just have to remember these, and whatever it is, if it is a now if you see this particular shunt motor, if it is a shunt motor, here we have series, and we know EB is equals to V minus IA RA. So because if you see, this is a shunt motor and V is appearing across field winding as well as the armature winding. Now V is equals to just nothing but EB minus whatever like V is nothing but EB plus drop across IARA. So EB is equals to V minus IARA. But if you see this in series motor, there is an additional field winding in series with the armature. Now if you want to write EB in series motor, how will you write V minus I? Because I is same as IA and ISC, that's what we wrote before. So I into RA, that is armature resistance, plus RSC, which is in series with the armature winding. Now this I is same as IA, ISC or IL, whatever it is, it's same. But here IA means only the current flowing through the armature winding. So yeah, so this is the shunt, and these are the back EMF equations for series and shunt motors. Yeah, so with that, so this is the basic introduction about the DC series motor and how a field winding is being placed in a DC series motor. And if a field winding is placed in series, how our back EMF equations change, and how our relation between back EMF and speed and flux, torque and field and current remain same. So those we discussed. And now let's solve a basic numerical, and which will help you understand DC series motor operation and principles more clear, and also it will be helpful to you in solving the assignment problems as well. Now let's see what was the data given and what we are asked to solve. So yeah, let me just read the question out. So a 200 volts DC series motor, where 200 volts you can say this is a terminal voltage. Whatever voltage they give inside in the question, if not mentioned, it is terminal voltage. 200 volt DC series motor, okay, series motor is given, and also terminal voltage is given. It has a total resistance. When we talk about total resistance, it's a summation of both armature resistance and field resistance. So for your understanding, it was already given in the question itself. That is, it is armature plus field. So it's 0.4. 0.4 is nothing but both RA and RSC. That's what you have to infer with the information given. Now what else was given? So it is given that it was taking 30 ampere current and driving a load at 800 RPM. So it was saying that when my DC series motor is driving a load at a speed of 800 RPM, it draws 30 ampere current from my supply. So that's the information. We are provided with the line current, which is same as series current, which is same as shunt series field winding current, which is same as the armature current. So 30 amps is being drawn from the supply, and the load is driving at a 800 RPM. Fine. So now extra information which is given: the load torque is proportional to the square of the speed. So the amount of torque which my load will draw is proportional to square of whatever the speed with which my load is driven. This is relation. So whatever relation, so it's a square of the speed. So there are constant torque loads, there are constant power loads, and this is such a load where my load torque is proportional to n square. One example is my everyone at your homes you will have the ceiling fans, right? So the fans are some example of this kind of load, which where the load torque is proportional to speed square, and there are some loads which load torque is proportional to just speed, proportional to n, not n square, and where some loads are there where my load torque is constant. Such loads you call constant torque loads, and some loads are there where they will require only constant power. So such loads are called constant power loads, or CPLs. So what you have to observe when you are solving a question is, what is your load type? How my load torque is varying with respect to any parameter. Here your load torque is varying with the speed, but the same speed, but in terms of power 2. So if your low torque changes 2 times, if your speed changes 2 times, your torque will change 4 times. So that's the proportionality relation it was given in the question. And the magnetization curve is linear, so it's linear, so there is no complexity. Your core is still in linear region, it's not saturated. And now it was saying that an additional 3.6 ohm resistance is connected in series with our existing machine. So now what happened, there is my motor, there is a series field winding, and to that we have added a series resistance of 3.6 ohms. Now that was all the data given, and what was asked from the question, that is estimate the new speed in RPM. We have to estimate new speed because previously it was rotating at a speed of 800 RPM. Fine. Now I have increased the resistance in series. Now I have to calculate the new speed. So what happens when you are connecting additional resistance? It means the drop will be more. Obviously, the speed should decrease. So we will see how much speed it is, but this is just a hunch. Whatever with the given data and whatever the given parameters, there is an additional resistance has been added to the circuit, and your speed should decrease. And we will see how we are going to find it. Now let's see. I'm dividing it into two parts. Before adding 3.6 external resistance and after adding the external resistance. Okay. Now before means whatever data it was given till this point. Okay. Now yeah, what is V? 200 volts as a total resistance. RA plus RSE, that is series resistance, is equals to, okay, 1 second, someone has joined. Yeah, now yeah, the total resistance means my armature and series resistance is 0.4, and it was taking a 30 amps. It is a series motor, so I'm just writing it as I. Let's say I1. I1 is equals to 30 amps, and driving at a load of N1 is equals to 800 RPM. Okay, this was all my previous data. And after before and after, what will remain same? Only my terminal voltage will remain same. So because that's a supply, that won't change. That is what you are feeding your motor. But armature plus field will change. Like armature plus field will remain same because that is only existing RA plus RSC. But R external is what changed. R external is 3.6 ohms, and I2 we don't know, N2 we don't know, because estimate the new speed. That's the thing asked. What is the new speed? Okay, this is what given. And before going into solving the question, let's just draw the picture how it looks like before and after. And then 1 second. Before and after, let's see how our machine will look like, and then we will proceed with solving. Now before, it's a series motor. My armature will be there here. This is my series motor, like series winding. That is my field winding. This is V, and RSE and RA, armature, back EMF, EB. Okay, these are my brush. And after, this is after adding external resistance. RSE plus R external. Okay. it's better if I write in terms of resistance only to avoid any confusion. Okay, RSE RA plus minus EB, and this terminal voltage will remain same. Yeah, so this external resistance is there. Yeah, now let's calculate this back EMFs in both cases. Now in before case, EB is equals to, we just wrote the equation in the previous slide, it is V. Now one more thing, it's a current I1 I2. Now I1 flows through RSE, RA and EB as well, so same current I1. So here the current is I2. Now you just write the equation for the back EMF in before case, that is V minus I1. What are the total resistances? RSE plus RA. RSE plus RA. Do you know all the parameters here? Yes, you know all the variables here. Not variables, all the parameters. V is 200 minus I1. I1 is 30, and total resistance component is 0.4. And yeah, how much is this?
180 ohm.
Okay, 180. Let me also calculate. 200 minus 12, 188. Yeah. Anybody else? Yeah. 188 volts. Correct. But if you want to calculate EB in this case, let's see, do we know all the parameters or not? I2 into what is the total resistance? RA plus RSE plus R external. So see that's a total that is the total amount of resistance present here, RA, RSE and external. So do you know all in this? Yeah, you know V, it is 200 minus I2, I don't know I2, and what is this total? RA plus RSE is 0.4 and R external is 3.6, it's 4. Now yeah, to calculate EB you need I2 here, so the rest you don't know, you just keep that aside. We will see later how we can calculate it. Now we will see how we will calculate the other part. We'll see how we will proceed. Okay, now one more relation we started a discussion today, that's the basic relation where EB is proportional to phi into omega, right? Where my phi, since it is a magnetic, my BH curve is linear, my whatever current that flows inside my field winding, that itself is responsible for the flux generated inside my field winding. So you can replace this flux with the amount of current flowing in the field winding. Now since this is a series motor, what is the current flowing in series winding, field winding? That is I1. Yeah, that means same, the same current which flows through series winding as well as armature winding is same. Now with that, now I can say EB is proportional to I into omega, that is field current into omega. Now this is my proportionality relation. Okay, now what I will do, proportionality EB1 by EB2 is equals to, in series motor what we have taken, I1 and I2, right? I1 omega 1 divided by I2 omega 2. Now in this, what else we know, what we know and what we don't know. We know W1 and I1, we don't know I2 and we don't know W2. So W2 is what asked in the question, but we know EB1 and EB2 which we calculated before. EB1 is 188, I will just write it here, 188, second. Okay, 188 divided by 188 divided by 200 minus 4i2. 200 minus 4i2, which is equals to I1 is how much? 30 multiplied by speed. First speed is 800 rpm. 800 divided by I2 I don't know, and omega 2 I don't know. Usually omega 2 we write in radians per second, but if it is in rpm we write it as capital N. So let's follow that notation. Now yeah, so this is what we have here, and what we will do is you cross multiply this, and we will get some relation. 188 I2 N2 is equals to, multiply this one for me, 48 into 10 power 5 minus 12 8s are 96 into 10 cube I2. So this is what we have from the equation, from the given data, and also back EMF principles, whatever we know from this relations, and equating that to the given data. This is what equation we got. But to calculate the new speed, which is N2, that is what required. You for this calculation of N2 you need I2, because in this equation there are two unknowns, but you have only one equation. You can't solve for N2 without the information about I2. Now you need some more data in order to solve this problem. Now let's go back to problem and let's see if there is any additional information which we didn't use. Now what else information is given? Series motor, total distance is 4.4, was taking 30 amps, load driving a load at 800. The load torque is proportional to square of the speed. So this particular relation which we haven't used, we know what kind of load I am driving, which is having such characteristics where my load torque is proportional to square of the speed with which my load is rotating. Now let's use that information as well, and let's see we can able to let's see whether that can help us in solving for the new speed. And yeah, let me just now load torque is proportional to n square, TL1 by TL2 is equals to n1 square by n2 square. Here the subscripts 1 and 2 denote what? The subscripts 1 and 2 denote, one is before adding external resistance, and N2, the number 2 is parameters after adding external resistance. The question asked was what is the speed after adding external resistance. So we are trying to solve it for N2. Now yeah, so this is what relation we that was given inside the question. But what we know, what's the information we know about the torque? TL is proportional to K phi IA, where we know this phi is nothing but, here you can see phi is proportional to IF if the curve is linear, because whatever current flows in my field winding will decide how much flux that will it produce. Now this is a series motor proportional to IF into IA. Now if you go to the basics what we started with, in a series motor IL is equals to IA is equals to ISC, that is the series current flowing in the series. Now if you see this relation, if you correlate that relation with our DC series motor, my torque load torque is proportional to IF multiplied by IA, but here both are equal, right, since it's a series motor. Now proportional to I square, where I is equals to IF is equals to IA. Now with that relation, I will write TL1 by TL2 is equals to I1 square by I2 square. So equation A, I got it from the data given in the problem, but equation B, I got it from the principles I know. What is the basic principle my DC machine will work? From that relation I got equation B, relation B. From the data given the problem I got the equation A. What is common in both A and B? The left hand side part is same, TL1 by TL2. Now I will equate these two equations A and B, and I will write from A and B, TL1 by TL2 is equals to N1 square by N2 square is equals to I1 square by I2 square. Now I1 square by I2 square is equals to N1 square by N2 square. So that's what relation we got. Now let's write it here only, no problem, it's the same problem. Now yeah, N1 square by N2 square is equals to I1 square by I2 square. Now what is N1? It is 800 RPM square divided by N2, I don't know. I1, this is the amount of current drawn, I30 square, and I2, I don't know again. Yeah. Now you solve this equation to get some relation. Squares only, all squares get cancelled. Okay. Now yeah, what else, what relation you will get? N2 is equals to 800 into I2 by 30, so 80 by 3, 26.666 I2. So let's say this is equation 2. Now what is equation 1 I have? So this is equation 1 I have. 188 I2 N2 is equals to 48 minus 96. Let me write that here. I'm not able to write. Once again. Okay. Okay.
Sir, N2 unit is turn RPM.
Sorry?
N2 units is RPM.
Yeah, N2 is in RPM. Because we know the value of N2 in RPM only. Let me write it in this mode only, because as soon as I'm making it full screen I'm losing 188. I'm writing it here. N2 I2 is equals to 48 into 10 power 5 minus 96 into 10 cube I2. See, now I have two equations. Previously I am having only one equation. Now I am having two equations with two unknowns. Those are N2 comma I2. Please solve these two equations and calculate the value of N2. So how can we get that? So substitute the value of I2. I2 is nothing but N2 by 26.66 in equation number 1. So 188 N2 multiplied by N2 divided by 26.66 is equals to 48 into 10 power 5 minus 96 into 10 cube. I2 is N2 divided by 26.66. So this is the quadratic equation in N2, or else you can substitute directly N2 as 26.66 I2 here. So you can also do that, or 188 into, in N2 you substitute I2, 26.66 I2 multiplied by I2 is equals to 48 into 10 power 5 minus 96 into 10 cube I2, and solve for I2. So this is again a quadratic equation in I2, where this is a square term, this is a single degree term, and this is a constant. And can someone solve and tell me the value of I2? In the calculators you will have how to solve a quadratic equation. Please solve with me. If you have these kind of calculators or gate calculators, I don't know, but these kind of calculators you will have the equation mode. You can give the coefficients there and you can get the answer. Now my square term is 188 into 26.66. Okay, my B term is first degree term, 96 1 2 3, and my constant term is minus 58 0 0 0 0 0. I got two values for I2. I'll just write those two here. One value is minus 41.96 amps, and second value is 22 plus 22.815 amp. Now from these two values, which would be the valid value for I2? Only positive value, because I2 minus and plus depends on the direction with which we took the convention. So if you see the diagram, I1 and I2 direction, if you see, that is from the supply to the machine. So that's how a motor direction should be. If it's a generator, the current should be towards the terminal voltage side V, but it's a motor, whatever convention we took, that is I should be moving going from the supply to the machine side. Then only you will get the drop EB minus IARA is equals to V. So whatever convention we took is correct. Our I2 should be a positive value. So with that inference, we can say that only I2 is 22.875 is the valid one. Now final value of I2 is equals to 22.815 amp. Now you know I2 and you know the relation between I2 and N2. So you take this particular I2, substitute I2 here, and you will get N2, where I'll just write it here itself. N2 is equals to 26.66 multiplied by 22.8. Can someone tell me how much it is? 26.6667 multiplied by 22.815. Whatever I am getting is, please tally, you also please tally. 608.4 RPM. Yeah, since N1 is in RPM, we will also have RPM N2. So that's what the relation we took. And yeah, now N2 we got. So that's the first question which was asked. So estimate the new speed. We know our new speed will be less than whatever speed it was rotating. What was the speed rotating? Before it was rotating at a speed of 800. Now our new speed is 608.4. Okay. Yeah. So this this is what our first question is. If you see the second question, what is our second question? Our second question is estimate the motor current. Estimate the new motor current is what is the motor current here? We don't talk about motor current, but always armature, series, field current and supply current. But what is motor current? Motor current is whatever current that is flowing through the motor. It is the armature current. Now if in the series motor, my armature current is same as my series current, which is same as the supply current. Now already we found that without even knowing the question itself, we solved that current in this problem itself, because we need the information of I2 in order to solve for N2. Now what is the new motor current? I2 is equals to 22.815. I just want to write here the conclusions. Okay. So before and after. So now we are done solving the question. I am just writing how change we have observed. Now before speed N1 is 800 RPM, and before current how much it is drawing? 30 amps. Now after, how much speed we got? 608.4 RPM. Now what is the new current? 22.8 22.81 amp. And yeah, all other rest of the parameters are same. The series and shunt winding and series and shunt winding in the new case are same, but what changed is external resistance. So we already started with the assumption that whenever we add a new resistance inside the like in series with the armature winding, that is an extra drop for the machine. So what some amount of power will be lost across that external winding. So the new speed and the new current drawn should be less. So that's what we saw from the result, that is N2 my new speed is 608 RPM, where my previous speed was 800 RPM, and my new current which is drawn by the supply is 22.81 amp, previously it was 30 amp. Now so that's what that's the last point I want to discuss today. And before ending today's session, I'm just going to brush our topics whatever we discussed today quickly. We started discussion with whatever topics we solved, we discussed for the past weeks inside the DC machines course. We started with the DC machines construction, armature winding and field winding, how they are placed, lap winding, wave winding, and some notations related to that windings. And then we moved to the derivations of back EMF and torque equations. We solved those equations right from the basic concepts of force inside a conductor area and all. With those concepts we solved those two equations, and those two equations came out to be EB is equals to K phi omega and torque is equals to K phi IA, and those are the fundamental equations for a DC machine. And then we moved to series shunt motor discussions. Before shunt motor we discussed the power flow diagrams as well. So inside a motor, what all losses we can see, right from input to the output, in between what are the losses. You know, there are copper losses, field copper losses, armature copper losses, and rotational losses, which is friction and windage losses as well as eddy current losses. So we discussed all this power flow till the shaft power available at the shaft. And then we move to DC shunt motor discussions. Shunt motor is where you will place the field winding in parallel with the armature and the supply, and this is the top figure you see right now on the slide, that is shunt motor, and the bottom one is series motor. Inside the shunt and series we solved a couple of numericals for each kind of model to get in touch with how this shunt motor works. And yeah, if you recall whatever we discussed today and also for the shunt motor case, the basic equations remain same, where EB is proportional to phi omega and torque is proportional to phi IA. So these are the basic equations. Whatever might be the winding, we use the same equation to solve. The only equations which will change is the back EMF equations. you have to be sure what current you are using if it is shunt, and what current you are using if it is a series. In series, you just saw all the currents are same, supply, series, and armature. But in shunt, supply current is different, armature current is different, and shunt current is different, because the current division takes place. The supply current is nothing but the summation of both armature and shunt. So that's the only thing you have to keep in mind. Apart from that, the basic concept remains same. Your EB is proportional to your flux generated because of the field current, and product is the product of flux generated by the field current and speed at which the machine rotates. And your torque developed in the motor depends on, it is proportional to the product of flux generated by the field current, that is phi. You replace phi with IF, is the product of IA, armature current. Again, this armature current is different for series and shunt. So and then for today we started with numerical, where we were given a DC series motor, and it was given, they have added an external resistance, and they asked us to find the new speed where the kind of load is, torque is proportional to square of the speed. Initially we know how to calculate back EMFs, and we arrived at one equation, that is equation number 1, which you see on the screen. And but with the load information, we arrived at equation B, that is equation 2, sorry. So there are two equations and the two unknowns. We substituted 1 in 2, and we carry on with the solution, and we got a quadratic equation, and then we solve those quadratic equation to get current value, the new motor current, and we substituted the new motor current in equation 2 to get the new speed. So that's how we solved. And this is the last point I want to discuss with you today. And if you have any kind of question in today's discussion, please do ask me. And if you have any questions apart from these concepts also, please do ask me. And if you don't remember right now, or if I can't solve that question, I will please raise those questions in the discussion forum, where all our TAs will be looking after that continuously. And any TA out of us, we will get back to you on the queries in the discussion forums. And don't forget to reach out to us, and don't forget to practice these numericals as many as possible, so that it will be easy for you to solve the assignment questions. And before ending today's session, I would like to request you to join the 7 p.m. session as well, where I have discussed only one concept of DC series motor and EMF and torque equations. But in that 7 p.m. session, we will be discussing some more concepts on DC series motor, which won't be clashing with today's discussion. So you are going to miss some concepts if you are going to miss the 7 p.m. session. So I request everyone to attend that session as well, and participate in the discussion. So please let me know if there are any questions for today in this topic discussed today. It's a pretty simple topic, a DC series motor and DC shunt motor. Overall, DC machines is a pretty simple topic if you understand the construction of winding and understand the derivations of back EMF and torque. Apart from that, it's just substitution and calculating for the asked parameters and data. So I request everyone to practice more and more problems on DC machines, and it will be easy for you to solve. So if you have no questions, I will end the session for today. 1 second.